The Great Pyramid was built in 20 years. That's one block every 2 minutes. And yet every pyramid built after it was worse, smaller, weaker, less precise than the first. This is not how civilizations learn. Mastery takes generations of trial and error, prototypes that fail, techniques that improve over time. But Egypt's greatest engineering achievement appeared suddenly, fully formed, with no practice runs before it. Then, for the next 2,000 years, Egyptian builders tried to copy it and failed. Tonight, we're going to examine why the timeline doesn't add up, why the oldest pyramid is the most advanced, and what that means about who really understood how to build them. The record shows the opposite. The most advanced pyramid is the oldest, and everything that came after declined in precision, in scale, in sophistication. Step closer to the stones themselves, and the accepted story begins to fracture. Across the plateau, the blocks weigh tens of tons. Some exceed 70. They fit together without mortar. Their surfaces ground so flat that modern engineers study the tolerances with admiration. The interior passages align with celestial markers. The dimensions encode mathematical constants that should not have been discovered for millennia. And beneath the surface, where sand and time have been stripped away, the bedrock itself tells a different story. Erosion patterns inconsistent with Egypt's dynastic climate. Subsurface weathering suggesting exposure during a wetter, older period. Foundations prepared long before the culture that claimed them. If you're settling in for this investigation, a like helps others find it. And in the comments, where are you listening from and what time is it there? The algorithm treats engagement like archival citation. It matters. What follows is not speculation. It's 10 claims, each one rooted in artifact, measurement, or administrative record. Each one presenting evidence that cannot be confirmed and cannot be dismissed. Too organized to be myth. Too strange to be history. We begin with the weight. The administrative archive from Egypt's 4th dynasty is exhaustive. Papyri catalog grain rations down to the loaf. Copper tool requisition schedules survive in triplicate. Worker shift rotations documented by scribe and season. Temple donation ledgers list offerings of bread, beer, livestock, linen, incense. The record shows what Egypt valued, what it tracked, what it preserved. But the record remains silent on one operation, how stones exceeding 70 tons were lifted to heights of 450 feet. The Great Pyramid contains approximately 2.3 million blocks. The bulk are limestone, averaging 2.5 tons, but the King's Chamber utilizes granite blocks weighing 50 to 80 tons each. These were quarried at Aswan, 500 miles south, transported by river, then moved across the plateau and raised into position at the pyramid's core, 150 feet above ground level. Modern cranes rated for 80-ton loads stand 200 feet tall, require reinforced concrete foundations, and operate with hydraulic systems and counterweight engineering developed over centuries. The 4th dynasty possessed none of this. The papyri list copper saws issued and returned. They note workmen absences for illness, rations withheld for lateness, bonuses distributed for festival days. They catalog the mundane with bureaucratic precision. But nowhere in the surviving administrative record is there a technical document, a work order, or a procedural manual explaining the methodology for moving megalithic stone. This is not a gap in preservation. Egypt recorded other complex processes in detail, Boat construction techniques appear in tomb reliefs with measurements and assembly sequences. Temple foundation rituals are described step by step in priestly texts. Metallurgical processes, smelting, alloying, tool forging, survive in workshop records. The silence around pyramid construction is selective, specific, and it compounds the engineering problem. The weight problem begins with mathematics. To construct the Great Pyramid in 20 years, the reign length attributed to Pharaoh Khufu requires placing 2.3 million blocks in 7,300 days. That's 315 blocks per day. Assuming a 10-hour workday, that's one block every 2 minutes. Not quarried every 2 minutes. Not transported every 2 minutes. Quarried, transported, dressed, positioned, and locked into place every 2 minutes for 20 years without interruption. The mathematics don't account for nighttime, seasonal flooding, religious festivals, tool maintenance, or worker illness. They assume perfect efficiency every day for 2 decades. The mainstream explanation invokes massive, coordinated labor, a workforce of 20,000 to 100,000, depending on the estimate. Rotating shifts during the Nile's flood season when agricultural work ceased. Ramps, straight, spiral, or internal, providing the inclined plane necessary to raise blocks incrementally. But the ramp hypothesis introduces its own paradox. A straight ramp to the pyramid's apex, maintaining a manageable 10% gradient, would need to extend over a mile in length. The volume of material required to construct such a ramp would exceed the volume of the pyramid itself. No debris field of this magnitude exists at Giza. No archaeological evidence of ramp demolition and disposal at the necessary scale. Spiral ramps, winding around the pyramid's exterior, solve the length problem but create new ones. They require constant adjustment as the pyramid rises, and their attachment points would leave scars on the pyramid's casing stones. The casing stones, mostly stripped in antiquity, but some remaining at the base, show no evidence of ramp anchorage. Internal ramps, theorized to rise through the pyramid's core, are invisible to archaeology but mathematically problematic. They consume internal volume, complicating the construction of chambers and passages, and once the pyramid is complete, the ramps must be dismantled from the inside, a process that risks destabilizing the structure. Each ramp theory solves one problem while creating others, and none address the fundamental question: where is the written record? Egypt imported Lebanese cedar for construction projects. The import ledgers survive. They list quantities, costs, transport manifests, storage assignments. If Egypt required timber for sledges, rollers, and ramp scaffolding on the scale necessary to build the Great Pyramid, the volume would dwarf typical construction needs. The cedar ledgers, when extrapolated against pyramid construction timelines, don't close. The quantities documented don't match the scale required. This is the pattern throughout. The tools are documented. The rations are documented. The labor villages are documented. But the method itself, the core technical process, is absent. Worker villages at Giza have been excavated. Mark Lehner's surveys in the 1990s identified housing, bakeries, breweries, and administrative buildings. The villages could accommodate 2,000 to 4,000 workers at a time. Well organized, well provisioned, evidence of a state-sponsored labor program. But 4,000 workers cannot place 315 blocks per day while also quarrying, transporting, dressing, and coordinating multi-ton stones. The mathematics require either a workforce 10 times larger, with no corresponding infrastructure, or a method that reduces labor needs by an order of magnitude. Neither explanation appears in the record. The inventory stela, a later inscription from Egypt's 26th dynasty, refers to Khufu as the pharaoh who restored the Great Pyramid, not built it. Mainstream Egyptology dismisses this as mythologizing by later scribes, but the language is precise. Restored implies prior existence, prior damage, prior knowledge. Later pyramids, constructed by pharaohs who explicitly attempted to replicate Khufu's achievement, are inferior. The Pyramid of Userkaf, 5th dynasty, collapsed partially during construction. The Pyramid of Neferirkare, also 5th dynasty, was never completed and relied on rubble fill to stabilize its core. 6th dynasty pyramids cracked, subsided, required mortar to bind smaller stones. These later builders had access to the same quarries, the same workforce systems, the same Nile transport routes. What they lacked was the method. If Egyptian engineering advanced incrementally, later pyramids should demonstrate refinement, improved techniques, enhanced precision. Instead, they demonstrate decline, degradation, forgetting. The toolmark evidence deepens the paradox. Granite blocks in the king's chamber show cutting precision that experimental archaeology struggles to replicate with copper saws and abrasives. Dennis Stocks, a researcher specializing in ancient Egyptian technology, conducted experiments in the 1990s using copper saws and quartz sand to cut granite. The results: one block required over 300 man-hours of labor. Multiple saw blades worn beyond usability, precision inferior to the Great Pyramid's finished surfaces. The Great Pyramid contains an estimated 8,000 granite blocks. At 300 hours per block, cutting granite alone would require 2.4 million man-hours, separate from quarrying limestone, separate from transport, separate from placement. Scaling Stock's experimental rate to the pyramid's timeline reveals an impossibility. Either the method was different or the timeline is wrong, or the workforce was vastly larger than the infrastructure supports. The archive does not clarify. It only catalogs what was consumed: bread, beer, copper, not what was accomplished. And what remains unexplained is this: why does a civilization that recorded grain taxation in obsessive detail leave no record of its most iconic achievement? Textual silence can be as revealing as inscription. Egypt chose not to explain the pyramids in writing. That choice, preserved across 4,500 years of administrative continuity, demands consideration. Later pharaohs left restoration records, not construction manuals. Restoration implies inheritance, knowledge received, not developed. The weight inventory paradox is not about missing data. It's about the presence of data that catalogs everything except the central claim. Too organized to be myth, too strange to be history. The record remains open, the ledger incomplete. But the weight problem is only the beginning. The precision problem is where the mathematics become impossible. The Great Pyramid's base covers 13 acres. Each side measures approximately 230 meters. The four corners form right angles within 0.05 degrees of geometric perfection. The base deviates from perfectly level by less than 2 centimeters across its entire expanse. 2 centimeters, over 230 meters. This is not ancient precision. This is modern precision. And it appears in a structure dated to 2580 BCE, then vanishes from the archaeological record for 2 millennia. The tolerance problem is not subjective. It's measurable. Laser surveying, conducted in the 1980s and refined through the 2000s, provides data that can be cross-verified by independent teams using GPS, photogrammetry, and theodolite measurements. The results converge. The pyramid's base is level to within 2.1 centimeters over 230 meters. For comparison, modern construction standards for large-scale projects consider plus 5 centimeters acceptable over similar distances. The Great Pyramid exceeds contemporary tolerances by a factor of 2. This precision is not isolated to the base. The ascending and descending passages inside the pyramid maintain angular consistency within 0.05 degrees over their entire length. The king's chamber walls are perpendicular to within 0.01 degrees. The casing stones, those few that remain intact at the base, fit together with seams averaging 0.5 millimeters, half a millimeter, between multi-ton blocks. Modern stone masons using laser-guided cutting equipment and diamond-tipped saws consider 1 to 2 millimeter tolerances professional grade. The Fourth Dynasty achieved half that. At scale, across 2.3 million blocks, using tools the official record lists as copper and stone. The question is not whether this precision exists. The measurements confirm it does. The question is how a civilization achieved it, without the instruments the precision requires. Leveling a 13-acre base to 2-centimeter tolerance requires either water leveling or optical surveying. Water leveling at this scale means flooding the entire base platform to create a reference surface, then cutting bedrock to match the water line. This technique is theoretically sound but logistically immense. The infrastructure would need to be trenches or channels cut into bedrock around the perimeter, a water source capable of filling 13 acres to measurable depth, and a method to prevent evaporation, seepage, and wind disturbance during the leveling process. No evidence of such infrastructure exists at Giza. No perimeter channels, no reservoir systems, no drainage networks scaled to handle 13 acres of controlled flooding. Optical surveying, using sighting instruments to establish level references, requires tools with precision optics. The Merkhet, a palm rib alignment tool used by Egyptian astronomers, could establish vertical and horizontal references for small-scale projects. But scaling Merkhet techniques to 13 acres with centimeter precision is mathematically dubious. The Merkhet works by sighting along a plumb line to celestial references. Useful for orientation. Less useful for micrometer-level elevation measurements across football field distances. Yet the base is level. The measurements confirm it. The method remains unclear. The precision extends beyond leveling. The pyramid's dimensions encode mathematical relationships that predate their formal discovery by millennia. The ratio of the pyramid's perimeter to its height approximates 2p, 2 times pi. Specifically, perimeter 921.5 meters, height 146.5 meters. The ratio is 6.229 compared to 2p Serhor 6.283, a deviation of 0.1%. Pi was not formally calculated to this precision until Archimedes in the 3rd century BCE, 2,300 years after the pyramid's construction. Egyptian mathematical papyri from the Middle Kingdom, 1650 BCE, approximate pi as 3.16, notably less accurate than the ratio embedded in the pyramid's dimensions. This presents two possibilities. Either the ratio is coincidental, the natural result of design choices unrelated to pi, or The builders worked from a mathematical template that encoded pi without documenting it in surviving texts. The second ratio is equally precise. The pyramid's slope angle, measured at 51.84 degrees, corresponds to the phi ratio, golden ratio F Serres 1.618, when applied to the relationship between the pyramid's height and half its base. This is the same ratio that appears in classical Greek architecture, Renaissance art, and modern studies of aesthetic proportion. Phi was formalized by Euclid around 300 BCE. The Great Pyramid encodes it 2,300 years earlier. Coincidence becomes statistically strained when multiple advanced constants appear in a single structure. Pi and phi, both embedded in dimensions, both predating their formal mathematical discovery by millennia. The mainstream explanation invokes aesthetic intuition. The builders, through trial and refinement, arrived at proportions that felt correct and happened to align with mathematical constants later discovered through formal geometry. This explanation assumes the constants emerged unconsciously, as byproducts of design rather than intentional encoding. It's possible. Humans do develop refined aesthetic sense through iterative craft traditions, but the explanation falters when considering the precision. A 0.1% deviation from 2p is not approximate. It's exact within the limits of ancient measurement. And phi's appearance in the slope angle is geometrically specific, not a loose approximation. If these ratios were unintentional, we would expect similar accidental encodings in other pyramids, other monumental structures, other Fourth Dynasty works. We don't. Later, pyramids lack these dimensional relationships. Earlier mastabas lack them. The precision appears once in the Great Pyramid, then fades. The degradation timeline is instructive. The Pyramid of Khafre, built by Khufu's successor, is slightly smaller, slightly less precise. Its base is leveled to within 5 centimeters. Still impressive, but 2.5 times less accurate than the Great Pyramid. The Pyramid of Menkaure, third of the Giza trio, is smaller still and less precise still. Base level tolerance degrades to 10 centimeters. Casing stone seams widen to 2 to 3 millimeters. By the 5th dynasty, a century later, pyramid construction quality collapses. The Pyramid of User-Kaf, intended as a grand project to rival Giza, partially collapsed during construction. Engineers resorted to rubble fill and mortar to stabilize the core. The casing stones fit poorly. The internal chambers show no astronomical alignments. If Egyptian engineering improved over time, if the Fourth Dynasty pyramids represented early experiments leading to later mastery, the quality trajectory should rise. Instead, it peaks immediately and declines continuously for 2,000 years. This is the tolerance paradox. Not just that the precision exists, but that it appears fully formed, is never equaled, and immediately degrades. The astronomical alignments deepen this paradox. The Great Pyramid's sides align to the cardinal directions, north, south, east, west, with an average error of 3 arc minutes, 0.05 degrees. This requires celestial observation and precise surveying, aligning to true north, not magnetic north, which shifts over time, requires tracking stellar positions over extended periods. The Egyptians likely used circumpolar stars, stars that never set below the horizon, to establish a north-south meridian. The technique is documented in later Egyptian texts, but executing it with 3 arc-minute precision requires not just observation, but mathematical correction for atmospheric refraction, stellar parallax, and the observer's latitude. These corrections were formalized in Hellenistic astronomy 1,000 years after the pyramid. Yet the alignment accuracy suggests they were applied or compensated for during construction. Inside the pyramid, the king's chamber contains 2 narrow shafts, each angled upward toward specific celestial targets. The southern shaft aligns with Orion's belt, as it appeared circa 2500 BCE. The northern shaft aligns with the pole star of that era, Alpha Draconis. These alignments are not approximate. They are geometrically precise, accounting for the Earth's axial precession, the slow wobble of Earth's rotational axis over a 25,920-year cycle. The shafts point to where the stars were in 2500 BCE, not where they appeared in later eras or earlier eras. This implies astronomical knowledge, sophisticated enough to track precession, or, at minimum, sustained observation campaigns across multiple generations to refine star positions to the necessary precision. The record does not catalog such observation campaigns. No astronomical logs from the 4th dynasty. No records of star charts or celestial measurement protocols. The knowledge is evident in the structure. The documentation is absent. Modern engineers study the Great Pyramid as a case study in tolerance engineering. University programs in structural engineering and surveying use its dimensions as teaching examples. The question posed to students is, how would you replicate this with modern tools? The answer generally involves laser levels, GPS surveying, computer-aided design, precision stone cutting with diamond saws, and construction coordination software. The tools we use to theoretically match 4th dynasty precision were developed in the 20th and 21st centuries. The question becomes, what tools did they use? Experimental archaeology attempts to answer this. Researchers build scale models using reconstructed ancient techniques. The results are informative. Copper saws can cut limestone slowly, with abrasive assistance. Stone pounders can dress block surfaces laboriously with skilled workers. Water and sand can polish granite eventually with sustained effort. But the experimental results don't match the pyramid's precision. They approximate it, close, but measurably inferior. This gap between experiment and artifact is the tolerance ledger's central entry. The precision exists. The method remains uncertain, and the precision appears once, then vanishes for 2 millennia. Too organized to be myth, too strange to be history. The measurements do not lie. Modern lasers confirm what ancient builders achieved. The question is not what was built. It's what knowledge built it. And whether that knowledge was developed over generations of trial and error, leaving incremental evidence in earlier structures, or inherited complete from a source the archive does not name. The record shows the latter. Perfection first, decline after. No apprenticeship phase, no improving trajectory. The tolerance ledger does not close. The precision remains. The explanation remains incomplete. But the mathematics gets stranger when you examine what's underneath. The Great Pyramid sits at latitude 29.9792458 degrees north. The speed of light in a vacuum, measured in meters per second, is 299,792 and 458 ms. The coordinate match is exact to 8 decimal places. This precision is not approximate. It is not close enough to be interesting. It is numerically identical when the degree symbol is removed and the comma is ignored. The latitude of the structure encodes the speed of light, a universal physical constant, not measured by human science until 1950, not defined as a fixed standard until 1983. The question is whether this is coincidence or encoding, and if encoding, what knowledge system produced it. The speed of light was first calculated with reasonable accuracy by Ole Rømer in 1676 through observations of Jupiter's moons. The value was refined over subsequent centuries using interferometry, atomic clocks, and quantum physics. In 1983, the meter was redefined based on the speed of light. Specifically, the distance light travels in 1,299,792,458 of a second. This definition makes the speed of light a fixed constant, exactly 299,792,458 meters per second by definition. The meter, previously defined by a platinum iridium bar in Paris, became a derivative of light speed and time measurement. The Great Pyramid was constructed circa 2580 BCE. The meter was invented in 1793 CE. The two are separated by 4,373 years, for the pyramid's latitude to encode the speed of light in meters per second requires either a coincidence of staggering statistical improbability or knowledge of Earth's dimensions, the meter, or an equivalent unit, and the speed of light 4,500 years before these values were measured. The mainstream explanation is coincidence. Given enough ancient structures and enough modern constants, some numerical matches will occur randomly. The human mind is pattern-seeking. We notice correlations and assign them significance even when none exists. This explanation is methodologically sound. Coincidences do occur. Pattern matching does generate false positives. The argument is not inherently dismissible, but it is testable. If the coordinate match is coincidental, similar matches should appear in other ancient structures when compared to other physical constants. They don't, at least not with 8-decimal precision. The Parthenon, the Colosseum, Stonehenge, Angkor Wat, Teotihuacan, none encode modern constants in their coordinates to 8-decimal places. Some show interesting numerical relationships when analyzed with sufficient creativity, but none demonstrate the precision of the Giza match. Statistical analysis of coincidence probability depends on the sample size and the specificity of the match. If we examine 10,000 ancient structures and compare them to 100 physical constants, the probability of an 8-decimal match occurring randomly is calculable. The calculation requires defining how many ancient structures exist, the sample size, how many modern constants are available for comparison, and how many decimal places constitute significant precision. For 8-decimal precision, the probability of a random match is approximately 1 in 100 million. This assumes the placement is random. If the placement is non-random, if the structure is deliberately positioned, the probability framework changes. The Great Pyramid is not randomly positioned. It sits at the center of Egypt's landmass. Its sides align to cardinal directions with 3 arc-minute precision. Its internal shafts target specific celestial objects. The placement is deliberate, engineered, and astronomically oriented. Deliberate placement reduces the likelihood of accidental coordinate encoding. If the builders chose the location for astronomical, geographical, or symbolic reasons, the latitude was fixed by those choices. The speed of light match would then be a byproduct of other design criteria. But this explanation assumes the builders did not know the latitude encoded the speed of light. It assumes ignorance rather than knowledge. And it does not explain why the coordinate match exists at all, coincidental or otherwise. The meter was defined using Earth's dimensions. Specifically, It was intended to represent 1/10,000,000th of the distance from the equator to the North Pole, along a meridian passing through Paris. Subsequent measurements refined the meter, and modern definitions use the speed of light. But the original intent was geodetic, based on Earth's size. For the pyramid's latitude to encode the speed of light in meters per second requires the builders to know Earth's circumference, the relationship between latitude and distance, the meter, or equivalent unit scaled to Earth's dimensions, and the speed of light. Earth's circumference was calculated accurately by Eratosthenes in 240 BCE, 2,340 years after the pyramid. He used shadow angles and distance measurements between Alexandria and Syene, modern Aswan, to estimate Earth's size within 2% accuracy. The calculation requires understanding that Earth is spherical, that sunlight arrives in parallel rays, and that angular differences in shadow length correspond to latitudinal arc distances. Eratosthenes had this knowledge. The fourth dynasty officially did not. But the pyramid's placement suggests otherwise. If the latitude is intentionally set to encode a constant, the builders knew Earth's dimensions well enough to calculate latitude to 8 decimal places. This requires geodetic surveying at a precision not formally documented until Hellenistic Greece. The speed of light is derived from Maxwell's equations, published in 1865, and measured using interferometry in the late 19th century. It is a fundamental constant linking electricity, magnetism, and the geometry of spacetime. There is no ancient text, no Egyptian papyrus, no cuneiform tablet that describes light as having finite speed, let alone calculates it. Yet the coordinate exists. The number is there. 29.979245 degrauhen, 8 decimal places, matching a constant discovered 4,500 years later. The precision is not approximate. GPS measurements of the Great Pyramid's apex, cross-verified by multiple survey teams using differential GPS with sub-centimeter accuracy, confirm the latitude to the necessary decimal places. The measurement is not disputed. The interpretation is. One counter-argument. The pyramid's original apex no longer exists. The capstone is missing. The current apex is eroded limestone, slightly lower than the original height. If the original apex was higher, the latitude would shift slightly. This is geometrically true, but the shift is minimal. Raising the apex by several meters, the maximum plausible capstone height, changes the latitude by approximately 1 degrees. This does not disturb the 8 decimal match. The coordinate remains within the speed of light encoding range. Another counter-argument. Latitude is a human convention. The equator is a natural reference, but the degree system, 360 degrees per circle, is arbitrary. Why would ancient builders use degrees? This argument conflates the coordinate system with the underlying geometry. Latitude measures angular distance from the equator. Whether expressed in degrees, radians, or any other unit, the geometric position is fixed. The coordinate 29.9979245 corresponds to a specific position on Earth's surface. That position is independent of the notation system. If the builders used a different angular system, the numerical encoding would differ, but the position would remain the same. And if they intended to encode the speed of light, they would choose a unit system that produced the desired match. The meter, as noted, is defined geodetically. It scales to Earth's dimensions. If the builders knew Earth's size and intended to encode the speed of light, They could derive a unit equivalent to the meter, position the structure at the appropriate latitude, and create the numerical match. This interpretation assumes knowledge, advanced knowledge, knowledge the official record does not document, or knowledge the official record encodes in structure rather than text. Elsewhere at Giza, numerical relationships proliferate. The three pyramids align with Orion's belt. The Great Pyramid's dimensions encode pi and phi. The king's chamber proportions reflect the Pythagorean theorem, 3:4:5 triangle ratios, 2,000 years before Pythagoras. Each relationship, considered individually, can be explained as coincidence or aesthetic intuition. Collectively, they suggest intentional encoding, mathematics embedded in stone. If the speed of light coordinate is part of this pattern, it represents the most sophisticated encoding, a constant unknown to human science until the modern era, embedded in a latitude determined 4,500 years ago. The knowledge required includes Earth's spherical geometry, precise latitude measurement, the speed of light as a finite constant, and a unit system scaled to Earth's dimensions. None of this appears in surviving Egyptian texts. The Rhind mathematical papyrus, dated to 1650 BCE, nearly 1,000 years after the pyramid, demonstrates Egyptian mathematics. It includes arithmetic, fractions, geometry, and practical problem-solving. The mathematics are sophisticated for their era, calculating areas, volumes, proportions. But the Rhind papyrus does not describe Earth as spherical. It does not calculate latitude. It does not mention light as having speed. The mathematics are practical, terrestrial, oriented toward taxation, construction, and trade. The pyramid's coordinate encoding, if intentional, represents a different order of knowledge, not practical mathematics. Theoretical physics, geodesy, constants embedded in cosmic structure. This knowledge does not appear in the papyri. It appears in the stones. The textual silence persists. The structural encoding persists, and the coordinate remains, 29.979245.8 degree 9, matching 299.792,458 mes to 8 decimal places, too organized to be myth, too strange to be history. The measurement exists. Independent verification confirms it. The statistical improbability of coincidence strains credibility. And the alternative, that the builders knew, requires revising the timeline of human knowledge by millennia. Neither explanation is comfortable. Both demand consideration. The coordinate precision matches a measurement made 4,500 years later, 8 decimal places, across 45 centuries. The placement knows something the builders, officially, should not. The archive does not explain. The stones do not clarify. The number simply exists, carved into geography by a structure whose purpose, method, and origin remain incompletely documented. The geodetic coordinate catalog does not close. The encoding remains. The knowledge source remains uncertain. But numbers can mislead. The testimony of workers cannot. The worker village at Giza was discovered in the 1990s by Mark Lehner and Zahi Hawass. The excavation revealed bakeries, breweries, fish processing facilities, copperworking shops, and dormitory-style housing. The infrastructure was substantial, well-organized, evidence of state-sponsored labor on an industrial scale. The village could house approximately 2,000 to 4,000 workers at maximum capacity. The Great Pyramid required moving 2.3 million blocks in 20 years. That's 315 blocks per day. 1 block every 2 minutes, 18 seconds, operating continuously 24 hours per day for 2 decades without interruption. The mathematics do not reconcile. This is not speculation. It is arithmetic applied to documented quantities. The pyramid's volume is known. The block count is estimated from dimensional analysis and internal structure surveys. The timeline is derived from historical records attributing the pyramid to Khufu's 23-year reign, conventionally shortened to 20 years of active construction. The ration problem begins with the worker village's capacity. Lehner's surveys identified sleeping quarters, food preparation areas, and administrative buildings sufficient for several thousand laborers. Cemetery analysis of worker burials nearby suggests a population consistent with this capacity, thousands, not tens of thousands. The daily block placement rate, 315 blocks per day, requires not just moving blocks, but quarrying them, transporting them, dressing them, positioning them, and integrating them into the rising structure. Each operation requires specialized labor: quarrymen, transporters, stonemasons, surveyors, engineers, overseers. If 4,000 workers operated in coordinated shifts, each worker would need to contribute to placing 0.079 blocks per day. That's 1 block per worker every 12 to 13 days. This seems manageable until the operations are decomposed. Quarrying a 2.5-ton limestone block requires cutting it free from bedrock, a process involving copper tools, wooden wedges, and pounding stones. Experimental archaeology suggests this takes 1 to 2 days per block with a crew of 4-6 workers. That's 6 to 12 man-days per block. Transporting the block from quarry to pyramid requires sledges, ropes, rollers, and coordinated teams. Estimates vary, but a 2.5-ton block pulled across sand and up ramps requires 20-50 workers depending on incline and distance. If transport takes 1 day, that's 20-50 man-days per block. Dressing the block, cutting it to precise dimensions, smoothing surfaces, fitting edges, requires skilled masons. Estimates suggest 2 to 4 man-days per block for rough dressing, more for precision casing stones. Positioning the block in the structure, lifting it into place, aligning it, verifying level and orientation, requires rigging crews, overseers, and surveyors. Add another 1-2 man-days. Summing conservatively, 10 man-days for quarrying, 25 man-days for transport, 3 man-days for dressing, 2 man-days for positioning. Total, 40 man-days per block. At 315 blocks per day, that's 12,600 man-days of labor required daily. If each worker contributes 1 man-day per day, standard labor accounting, the workforce needs to be 12,600 workers. The village housed 4,000. The deficit is 8,600 workers. Where were they? The mainstream explanation invokes seasonal labor. During the Nile's annual flood, from July to October, agricultural work ceased. Farmers became available for state labor projects. This rotating workforce could swell to 20,000, 50,000, or even 100,000, depending on the estimate. The explanation is logistically plausible. Egypt's population during the 4th dynasty is estimated at 1 to 2 million. Mobilizing 5 to 10% of the population for seasonal labor is feasible. Rome did it. China did it. Large-scale state projects throughout history relied on corvée labor systems. But the seasonal labor explanation introduces new problems. If construction occurred only during the 4-month flood season, the annual work window shrinks to 120 days. The 20-year timeline becomes 2,400 working days, not 7,300. The daily block placement rate increases from 315 to 958 blocks per day, nearly 1 block every 90 seconds. This is not feasible. The bottlenecks multiply. Quarrying cannot keep pace. Transport logistics collapse. The ramps become congested with thousands of workers attempting to move nearly 1,000 blocks daily up inclines that narrow as the pyramid rises. The alternative is year-round construction with a permanent workforce. This returns to the original problem. Where are the workers? The cemetery evidence compounds the issue. Worker burials near the pyramid site number in the thousands, not tens of thousands. The graves show evidence of labor-related injuries, fractured bones, compressed vertebrae, repetitive strain markers. These are consistent with heavy construction work. But the burial count suggests a workforce of several thousand over the pyramid's construction period, not the 20,000 plus required by the mathematics. Cemetery populations do not capture entire workforces, especially if workers rotated in and out. But the burial count should scale proportionally. If 20,000 workers labored for 20 years, and assuming a 2% annual mortality rate, conservative for heavy labor, we would expect 8,000 burials. The discovered cemeteries contain a fraction of that. The ration records create another constraint. Papyri fragments from the 4th dynasty document bread and beer allocations. Bread was the staple. Workers received rations based on status. Skilled workers, unskilled workers, overseers. The quantities are documented. Extrapolating these rations to a 20,000-person workforce over 20 years requires grain production on a massive scale. Egypt's agricultural output is estimable from later tax records and land surveys. The Nile's flood cycle determined planting and harvest schedules. Grain yields per acre are known from comparative studies. The extrapolation suggests Egypt could sustain a large workforce, but the grain storage and distribution infrastructure required would leave archaeological traces. Granaries, transport facilities, administrative centers. The scale should match the labor scale. The discovered infrastructure at Giza supports several thousand workers, not 20,000, not 50,000. The bakeries, breweries, and storage facilities are substantial but not proportional to the larger workforce estimates. This is the ration deficit. The calories don't scale to the labor requirements. The bread issued, when calculated against the blocks moved, suggests either the workforce was smaller and used unknown methods, or the timeline is wrong, or the infrastructure has not been fully discovered. Bread ration ledgers survive in meticulous detail. They catalog daily distributions, account for worker absences, note shortages and surpluses. The bureaucracy was thorough. If 20,000 workers labored for 20 years, the bread consumption would be documented at proportional scale. The documented ration quantities, when scaled, suggest a workforce of several thousand, consistent with the village capacity, consistent with the cemetery population, inconsistent with the block placement mathematics. 1. Resolution. The block placement rate is inflated. Perhaps the pyramid took longer than 20 years. If construction extended to 40 years, the daily rate drops to 158 blocks per day. The workforce requirements have, but extending the timeline contradicts the precision. The pyramid's construction shows no evidence of technique drift, no stylistic evolution, no interruption in planning. The structure is coherent, unified, executed according to a single master plan. This suggests continuous, sustained construction, not a multi-generational project with shifting methods. Later pyramids, built over extended periods by multiple pharaohs, show discontinuities, changes in casing stone quality, shifts in internal chamber design, evidence of plan revisions. The Great Pyramid shows none of this. It reads as a single, uninterrupted project. If the timeline extends, the coherence becomes harder to explain. If the workforce shrinks, the mathematics become harder to explain. The deficit remains. The ledger does not close. The village infrastructure, the cemetery population, and the ration records all converge on a workforce of several thousand. The block placement mathematics require tens of thousands. The gap is not marginal. It's an order of magnitude. Experimental reconstructions attempt to close this gap. Research teams build scale models using reconstructed ancient techniques. They measure time per block, workers per task, coordination overhead. The experiments provide valuable data. But the experiments consistently show that replicating the pyramid's construction rate requires either larger workforces than the infrastructure supports, or methods not documented in the archaeological record, or timelines longer than the pyramid's coherence suggests. The experiments do not fail because researchers lack ingenuity. They fail because the documented constraints, tools, techniques, workforce capacity do not produce the documented outcome within the documented timeline. This is the ration deficit's implication. Either the constraints are wrong, we misunderstand the tools, the techniques, or the capacity, or the outcome is wrong. The pyramid took longer or used different methods, or the record is incomplete. Infrastructure and methods existed but left no trace. Each possibility revises the standard narrative. None can be confirmed. None can be dismissed. The bread issued is documented. The blocks placed are documented. The mathematics connecting them do not close. The deficit is measurable, persistent, and unexplained by the surviving record. Too organized to be myth. Too strange to be history. The ledger shows how much bread was issued, not how the stones moved. The village housed thousands. The pyramid required tens of thousands. The ration calculations do not account for the workforce the timeline demands, and the ration deficit is administrative. The copper deficit is metallurgical. Copper is soft. On the Mohs hardness scale, copper rates 3.5 to 4. Limestone, the primary material of the Great Pyramid, rates 3 to 4, comparable to copper. Granite, used in the king's chamber and internal passages, rates 6 to 7. Copper cannot cut granite without assistance. This is not theoretical. This is materials science. A softer material cannot abrade a harder material without an intermediary abrasive. The experimental evidence is extensive, documented, and publicly available. Dennis Stocks, a British Egyptologist specializing in ancient technology, conducted systematic experiments in the 1980s and 1990s to replicate ancient Egyptian stoneworking techniques. His methodology was rigorous. Reconstructed copper saws based on tomb illustrations, quartz sand as abrasive, granite blocks sourced from Aswan quarries. The results are measurable. Cutting a single granite block, approximately 1 cubic meter, with a copper saw and sand abrasive required 300+ man-hours. Multiple saw blades wore beyond usability during the process. The cut precision was inferior to the surfaces found in the Great Pyramid's King's Chamber. The Great Pyramid contains an estimated 8,000 granite blocks. These blocks form the King's Chamber walls, ceiling beams, internal passages, and structural reinforcements. Each block weighs between 25 and 80 tons. Each required cutting, dressing, and transport from Aswan, 500 miles south. At Stock's experimental rate, 300 hours per block, cutting 8,000 granite blocks requires 2.4 million man-hours of sawing alone. This is separate from quarrying, separate from transport, separate from positioning. This is only the cutting operation. If the pyramid is built in 20 years, that's 7,300 days. Dividing 2.4 million hours by 7,300 days yields 329 hours per day. If each worker operates a saw for 10 hours per day, the operation requires 33 workers sawing granite continuously for 20 years. This seems manageable until the tool consumption is factored in. Stock's experiments destroyed multiple copper saw blades per block. Copper is soft. Granite is hard. The abrasive sand wears the copper as it cuts the granite. The saw blade thins, weakens, and eventually fails. Replacing the blade requires new copper, smelting, forging, and delivery to the worksite. At one saw blade per block, a conservative estimate, cutting 8,000 granite blocks requires 8,000 copper saw blades over 20 years. That's 400 blades per year, or roughly one blade every day. Copper smelting requires ore, fuel, furnaces, and skilled metallurgists. Egypt sourced copper primarily from the Sinai Peninsula, where mining operations are archaeologically documented. The scale of copper production during the Fourth Dynasty is estimable from mine evidence, slag heaps, and tool inventories. The estimates do not account for 8,000 saw blades, plus the thousands of chisels, drills, and other tools required for limestone work, infrastructure maintenance, and general construction. The copper supply chain is documented in administrative texts. Copper tool requisitions appear in papyri. Tools issued to work crews, tools returned after use, tools lost or damaged and replaced. The bureaucracy tracked this. But the documented quantities, when scaled against the pyramid's granite cutting requirements, do not close. The copper consumption implied by the experimental replication exceeds the copper production documented in the archaeological record. This is the copper tool inventory gap. The tools are shown in tomb paintings. The saws are real. The technique is demonstrated. But the scale does not match the outcome. The mainstream explanation invokes efficiency improvements. Perhaps Fourth Dynasty workers developed techniques that reduced cutting time, extended blade life, or minimized copper waste. Perhaps the experimental reconstructions, conducted by modern researchers, do not replicate the skill level of ancient specialists. This explanation is plausible. Craft knowledge improves with practice. A worker sawing granite daily for years develops efficiency that a modern researcher, conducting short-term experiments, does not achieve. But efficiency gains are incremental, not exponential. If Stock's 300-hour per block rate could be halved through superior technique, the time drops to 150 hours per block. The copper consumption drops proportionally. The gap narrows but does not close. The inventory gap persists because the scale is wrong, not by a factor of 2, by a factor of 10 or more. No industrial-scale copper working site has been discovered at Giza. Smelting furnaces, slag heaps, tool manufacturing debris. These leave archaeological traces. Copper production generates waste, ore tailings, charcoal ash, failed castings, broken molds. Large-scale metalworking operations, such as those required to produce thousands of tools over 20 years, create debris fields proportional to the output. Roman ironworking sites in Britain left slag heaps visible for millennia. Bronze Age tin smelting in Cornwall left identifiable waste deposits. Giza shows evidence of copper tool use, individual tools, small-scale repairs, workshop areas, but not the industrial output the granite cutting requirements demand. One counter-argument. The debris was removed. Egyptians cleaned work sites, recycled materials, and transported waste elsewhere. Absence of evidence is not evidence of absence. This is methodologically correct. Archaeological absence proves nothing. Sites degrade, are looted, are built over. Evidence disappears. But the absence here is not isolated. It compounds the other absences. No construction manuals, no ramp debris at scale, no workforce infrastructure at scale, no copper production at scale. Each absence, individually, can be explained. Collectively, they form a pattern. The pattern suggests either the scale is overestimated, the pyramid required less labor, fewer tools, less copper than calculations suggest, or the methods were different from those documented in the archaeological record. Tomb paintings show copper saws. Tomb paintings are evidence, but tomb paintings are also idealized representations, not technical documentation. They show what ought to happen, not necessarily what did happen. They depict ritual, divine authorization, symbolic correctness. The paintings show workers pulling sledges, operating saws, pounding stones. These are real techniques, but the paintings do not show the scale, the timeline, or the logistical complexity. They compress years of work into single, static images. Using tomb paintings as technical manuals is similar to using religious iconography as engineering diagrams. The information is present but incomplete, symbolic rather than procedural. The tool mark evidence on pyramid stones provides more direct data. Granite blocks in the king's chamber show striations consistent with sawing. The patterns are regular, parallel, indicative of blade passage through stone. This confirms sawing occurred, but the tool marks do not specify the blade material. Copper leaves marks. So does bronze. So does harder stone used as an abrading edge. The marks confirm the action, not the tool composition. Some researchers have proposed that Egyptians used harder materials, dolerite pounders, emery abrasives, or lost techniques involving materials that decompose and leave no trace. These proposals are speculative but not dismissible. Dolerite, a hard igneous rock, is found in Egyptian tool assemblages. Pounding with dolerite can shape granite slowly through percussive fracturing. This technique requires no metal, leaves no blade marks, and produces irregular surfaces. But the king's chamber surfaces are not irregular. They are flat, smooth, indicative of sawing or grinding, not pounding. The technique required for the observed finish is different from dolerite percussion. Emery, an abrasive mineral harder than granite, could theoretically be used with softer blades to cut harder stone. The abrasive does the cutting. The blade is merely the carrier. This would extend blade life and reduce copper consumption, but emery sources in Egypt are limited. No large-scale emery quarrying or processing sites have been identified from the 4th dynasty. The material exists in the region, but not in quantities proportional to 8,000 granite blocks. The lost technique hypothesis proposes that 4th dynasty Egyptians possessed methods later forgotten: organic abrasives, chemical treatments, acoustic resonance cutting. These methods left no archaeological trace because they used perishable materials or processes that do not fossilize. This hypothesis is unfalsifiable. It can explain any anomaly by invoking unknown methods. Methodologically, it is weak because it replaces documented uncertainty with speculative certainty. But the hypothesis cannot be entirely dismissed. Civilizations do lose knowledge. Techniques disappear when practitioners die without apprentices. Technologies become obsolete and are forgotten. The historical record is full of lost methods: Greek fire, Roman concrete formulations, Damascus steel techniques. If 4th Dynasty Egypt possessed stone-cutting methods later lost, this would explain the copper inventory gap. The tools shown in tomb paintings are symbolic representations of conventional methods, while the actual techniques used something else. This interpretation aligns with the pattern of textual silence. Egypt recorded what it wanted to record. It did not record its most sophisticated techniques. The paintings show copper saws because saws are understandable, conventional, appropriate for symbolic representation. The actual method remains undocumented. The copper consumption remains unaccounted for. The inventory gap remains open, too organized to be myth, too strange to be history. 300 hours per block, 8,000 blocks. The calculations are simple. The results do not match the archaeological evidence of copper production. The tools are shown. The technique is demonstrated. The scale does not reconcile. The mine ledgers don't account for the volume. The paintings show the saw, not the impossible mathematics. The tool marks confirm cutting occurred. The copper inventory does not confirm how, and the copper problem is practical. The alignment problem is celestial. The Great Pyramid contains 2 narrow shafts, extending from the king's chamber at precise angles through hundreds of feet of solid masonry. These are not ventilation shafts. They do not reach the exterior. They terminate within the pyramid's mass, pointing toward specific celestial targets. The southern shaft angles upward at approximately 45 degrees, aligned to Orion's belt as it appeared at its culmination point circa 2500 BCE. The northern shaft angles at approximately 32 degrees, aligned to Alpha Draconis, Thuban, the pole star of that era. These alignments are not approximate. They are astronomically precise, accounting for Earth's axial precession. Precession is the slow wobble of Earth's rotational axis over a 25,920-year cycle. This wobble causes the apparent position of stars to shift gradually over centuries. The pole star changes. The zodiac constellations drift through the calendar. Ancient sky maps do not match modern sky maps because the reference frame has rotated. Thuban was the pole star in 2500 BCE. By 1500 BCE, it had drifted. By modern times, Polaris holds that position. The shift is measurable, predictable, and requires long-term astronomical observation to detect. The pyramid's northern shaft points to where Thuban was 4,500 years ago, not where it is now, not where it was in earlier eras. The alignment is epoch-specific, locked to the sky of the 4th dynasty. This requires either sustained astronomical observation over multiple generations to track precession, or inherited star charts from earlier observers who had already measured it, or coincidental alignment that happens to match 2500 BCE, despite being intended for a different purpose. The coincidence explanation falters when both shafts are considered together. The southern shaft targets Orion's belt. Also at its 2500 BCE position, two independent celestial alignments, both epoch-specific, both precise, occurring in the same structure. The probability of dual coincidence is the product of individual probabilities. If each alignment has a 1 in 100 chance of being coincidental, the combined probability is 1 in 10,000. These are illustrative numbers. Actual probabilities depend on angular tolerances and targeting criteria, but the principle holds. Multiple precise alignments compound improbability. The mainstream explanation invokes ritual astronomy. The Egyptians observed the stars for religious purposes. Orion was associated with Osiris, god of the afterlife. Thuban marked the celestial north, symbolically important for pyramid orientation. The shafts were soul passages, allowing the deceased pharaoh's spirit to ascend to the stars. This explanation is culturally plausible. Egyptian religion did connect specific stars with deities. Funerary texts describe the deceased ascending to join Orion and becoming one with the imperishable stars, the circumpolar stars that never set. But ritual purpose does not preclude astronomical precision. The two are compatible. A shaft intended as a soul passage can also be an astronomical instrument. The cultural meaning and the technical achievement coexist. The question is, how did Fourth Dynasty astronomers achieve the precision? Tracking precession requires comparing star positions across long time periods. A single generation of observers sees negligible shift. Precession moves the pole star by approximately 1 degree every 72 years. To detect this, observers must maintain records across multiple lifetimes, comparing measurements separated by centuries. No such records survive from Fourth Dynasty Egypt. No star catalogs, no observational logs, no astronomical tables. The administrative archive that preserved grain rations and copper tool inventories contains no astronomical data. Later, Egyptian astronomical texts, deacons, star clocks, temple ceiling maps, date to the Middle Kingdom, and later. These texts are practical, tracking time at night, determining festival dates, aligning temples. They do not describe precession or reference long-term stellar drift. Greek astronomers documented precession. Hipparchus, working in the 2nd century BCE, compared his observations to star positions recorded by earlier Greek and Babylonian astronomers. The comparison revealed systematic shifts, which Hipparchus correctly attributed to precession. Hipparchus had access to earlier records. Babylonian astronomical tablets provided centuries of data. The comparison was possible because the data was preserved, cross-referenced, and transmitted across generations. Fourth Dynasty Egypt has no equivalent dataset. The pyramid's shaft alignments suggest precession was known, but the documentary evidence of that knowledge is absent. One interpretation: the knowledge was observational rather than mathematical. Astronomers tracked Thuban's position through direct sighting over decades. When the pyramid was designed, they aligned the shaft to the current pole star position, without calculating precession. They simply recorded where Thuban was at that moment. This explains the 2500 BCE alignment without requiring long-term precession awareness. The shaft points to Thuban because Thuban was the pole star when the shaft was constructed. No advanced knowledge needed, just real-time observation. But this interpretation does not explain the Orion alignment. Orion's belt is not circumpolar. It rises and sets. Its position changes throughout the night and throughout the year. Aligning a shaft to Orion requires choosing a specific moment. Which night? Which hour? Which point in Orion's arc across the sky? The southern shaft targets Orion's culmination, the highest point in its nightly arc. This is the moment when Orion crosses the celestial meridian, the imaginary line running from north to south through the zenith. Culmination is astronomically significant, a natural reference point. But selecting culmination as the target requires understanding meridian transit, celestial mechanics, and the relationship between Earth's rotation and stellar motion. This is not casual stargazing. This is positional astronomy. The shaft's angle, 45 degrees from horizontal, corresponds to Orion's altitude at culmination, as seen from Giza's latitude in 2500 BCE. The alignment is geometrically exact. Pyramid latitude, shaft angle, and Orion's declination form a closed trigonometric relationship. Achieving this requires calculating Orion's declination, its angular distance from the celestial equator, knowing Giza's latitude, and setting the shaft angle to match. This is spherical astronomy, formalized by Greeks and Arabs millennia later. Unless the alignment is coincidental, unless the shaft angle was chosen for structural reasons, load distribution, passage clearance, symbolic geometry, and happens to align with Orion by chance. Testing coincidence requires examining other pyramids. If stellar shaft alignments are common, the pattern suggests intentional design. If unique to the Great Pyramid, coincidence becomes more plausible. Other pyramids contain shafts, but none demonstrate the same precision. The Pyramid of Khafra has no interior shafts targeting stars. The Pyramid of Menkaure has chambers but no astronomically aligned passages. Later, pyramids abandoned the shaft design entirely. The Great Pyramid's shafts are unique. Precision achieved once, then not replicated. This pattern recurs. Dimensional precision, achieved once, then degraded. Astronomical alignment, achieved once, then abandoned. Construction scale, achieved once, then reduced. If these achievements resulted from gradual refinement, later pyramids should maintain or exceed them. Instead, they decline immediately. Knowledge demonstrated once, then lost. The Orion correlation extends beyond the shafts. Robert Bauval's theory, proposed in the 1990s, suggests that the three Giza pyramids map the three stars of Orion's belt on the ground. The alignment is not perfect. The smallest pyramid, Menkaure, is offset slightly, but the correlation is strong. Bauval also noted that the alignment was most accurate not in 2500 BCE, but in 10,500 BCE, when Orion reached its lowest point in the precessional cycle. At that date, Orion's belt stars matched the pyramid layout with higher precision, and the Milky Way's position mirrored the Nile's course relative to the pyramids. This interpretation is controversial. It suggests the Giza site plan was designed in 10,500 BCE, 7,000 years before dynastic Egypt, and the pyramids were later constructed according to a pre-existing astronomical blueprint. Mainstream Egyptology rejects this. The pyramids are securely dated to the 4th dynasty through multiple lines of evidence: carbon dating of organic materials, pottery typology, inscriptional evidence, architectural progression. Bauval's response: the structures are 4th dynasty, but the plan is older. The Egyptians built according to a layout inherited from predecessors who surveyed the site millennia earlier. This interpretation reconciles the astronomical evidence with the archaeological evidence. The precession knowledge, the site alignment, the geodetic encoding all point to ancient surveying. The construction, the inscriptions, the architectural style all point to Fourth Dynasty execution. The two timelines collapse into one: planning in deep antiquity, construction in dynastic history. This interpretation cannot be confirmed. It also cannot be dismissed. The astronomical alignments exist. The 10,500 BCE correlation is mathematically precise. The precessional knowledge implied by the alignments is not documented in Fourth Dynasty texts. Either the knowledge was developed independently by Fourth Dynasty astronomers and subsequently lost, or it was inherited from earlier surveyors whose work predated written records. Both possibilities revise the standard narrative. Both require explaining how astronomical knowledge of this sophistication appeared suddenly, achieved precision unmatched for millennia, and then vanished without textual documentation. The shafts themselves were discovered through modern surveying. Ancient visitors to the pyramid's interior would not have known they existed. The passages are too narrow for human access, blocked by stone, invisible from the chambers. Why construct passages no one can traverse, aligned to stars no one inside the pyramid can see? The ritual explanation. Symbolic pathways for the pharaoh's soul. The passages need not be functional for living humans. They function spiritually, connecting the burial chamber to the imperishable stars. The astronomical explanation. Observational instruments or alignment markers used during construction, later sealed within the structure. The shafts served a practical purpose initially, then were incorporated into the pyramid's mass. Both explanations are plausible. Neither is provable. The shafts exist. Their alignment is precise. Their purpose remains interpretive. What is not interpretive is the astronomy. The angles are measurable. The star positions are calculable. The match between shaft angle and celestial target is confirmable through spherical trigonometry and precession models. The alignment was perfect 7,000 years before Khufu. The stars moved. The pyramids remember where they were. Too organized to be myth. Too strange to be history. Someone mapped a sky that dynastic Egypt never saw. Someone encoded that map in stone, in passages sealed within the pyramid's core, aligned with a precision that required either long-term observation or inherited star charts. The record does not catalog centuries of astronomical observations. The papyri remain silent. The shafts remain aligned, and the knowledge remains unexplained. But the stars may lie in interpretation. The papyri do not. Egypt preserved more than 50,000 papyrus documents across 3 millennia. The archive is exhaustive. Tax assessments, temple donations, worker complaints, grain inventories, copper tool requisitions, legal disputes, marriage contracts, funerary prayers, medical prescriptions, astronomical observations of later periods, administrative minutiae catalogued with bureaucratic precision. The archive records almost everything, except one thing. Not a single technical document explains how the pyramids were built. No blueprints, no engineering manuals, no step-by-step procedural texts, no diagrams showing ramp construction, stone lifting apparatus, or surveying methods, no master plans indicating chamber layouts, passage angles, or dimensional specifications. The absence is total. And it is not random. Egypt recorded complex processes in detail when it chose to. Boat construction manuals survive, showing hull assembly sequences, plank dimensions, joinery techniques, Temple foundation rituals are described in priestly texts with precise instructions: where to dig, what offerings to make, how to orient the structure to cardinal directions. Metallurgical processes appear in workshop records: copper smelting temperatures, alloying ratios, tool forging sequences. The knowledge was written down, transmitted, preserved. But pyramid construction, the civilization's most iconic achievement, the largest stone structures in the ancient world, monuments that required decades of coordinated labor and sophisticated engineering, left no written methodology. This is not preservation failure. Papyri survive from earlier periods and later periods in comparable environmental conditions. The Nile Delta's humidity destroys organic materials, but documents from Upper Egypt, stored in tombs and temple libraries, endure for millennia. The mathematical papyri survive. The Rhind mathematical papyrus, circa 1650 BCE, contains 84 problems covering arithmetic, geometry, and practical calculations. Problems include computing pyramid slopes, calculating grain storage volumes, and determining land areas after Nile flooding. The Moscow mathematical papyrus, circa 1850 BCE, includes the formula for calculating a truncated pyramid's volume, a formula directly applicable to pyramid construction. The knowledge existed. It was written down. But it was written 500 to 1,000 years after the Great Pyramid, describing mathematics that should have been used during its construction. Why does the mathematical knowledge appear in texts written centuries after the structures that required it? One explanation: the knowledge was transmitted orally. Craft guilds, priestly schools, and specialized workshops preserved techniques through apprenticeship. Master builders trained successors. The knowledge passed from generation to generation without requiring written manuals. This explanation is culturally plausible. Many traditional crafts operate this way. Oral transmission can preserve complex information across centuries. Indigenous cultures worldwide maintain detailed knowledge systems without written texts. But oral transmission has limitations. It is vulnerable to disruption. When guilds disband, when practitioners die without successors, when invasions or plagues interrupt transmission, the knowledge is lost, and the knowledge was lost. Fifth dynasty pyramids demonstrate technical decline. Sixth dynasty pyramids collapse. By the Middle Kingdom, pyramid construction has largely ceased, replaced by rock-cut tombs. The techniques degraded within centuries, suggesting oral transmission was incomplete or interrupted. If the knowledge was considered too valuable to risk losing, why not write it down? Egypt wrote down everything else. Medical texts preserve surgical procedures. Agricultural texts describe irrigation management. Legal texts codify property rights. The selective silence around pyramid construction is deliberate. Egypt chose what to document, and it chose not to document this. One interpretation: the knowledge was sacred, restricted to initiated specialists, forbidden from general circulation. Writing it down would profane it, make it accessible to the unworthy, violate religious prohibitions. This interpretation aligns with Egyptian culture. Sacred knowledge was guarded. Temple mysteries were restricted. Priestly texts encoded esoteric wisdom accessible only to initiates. Secrecy was a feature, not a flaw. But pyramid construction involved thousands of workers: quarrymen, transporters, masons, surveyors, overseers. These were not all initiates. Most were seasonal laborers, rotating in and out. The workforce was too large, too transient to maintain strict knowledge secrecy. Unless the secret knowledge was not the labor itself, but the master plan. The workers executed tasks. Cut this stone, move it here, position it there, without understanding the overall design. Only the architects, the master builders, possessed the complete vision. This model is hierarchical, knowledge stratified by role. Workers need practical skills. Architects need comprehensive understanding. Only the architect's knowledge is sacred, restricted, undocumented. If this model is correct, the loss of knowledge occurs at the top, not the bottom. When master architects die without trained successors, the master plan is lost even if practical skills persist. Later, builders retain the ability to cut stone and build walls but lack the geometric, astronomical, and engineering sophistication to replicate the Great Pyramid's design. This explains the degradation timeline. Practical knowledge persists. Fifth Dynasty pyramids still employ stone cutting, ramp systems, labor coordination. But design sophistication declines, proportions degrade. Astronomical alignments are abandoned, dimensional encoding disappears. The papyrus silence extends beyond construction manuals. Historical accounts are also sparse. The only detailed description of pyramid construction comes from Herodotus, writing in the 5th century BCE, 2,000 years after the 4th dynasty. Herodotus visited Egypt, interviewed priests, recorded what he was told. His account describes 100,000 workers rotating in 3-month shifts, laboring for 20 years. It describes machines made of short wooden planks that lifted stones from level to level. It describes Khufu as a tyrant who enslaved his people and bankrupted the kingdom. This account is second-hand testimony, transmitted across 2 millennia. The priests Herodotus interviewed were not eyewitnesses. They were repeating traditions, stories, perhaps legends filtered through countless retellings. The account contains details that may be accurate: the 20-year timeline, the large workforce, the use of lifting devices. But it also contains elements that seem symbolic or moralistic: the tyrannical pharaoh, the national exhaustion, the excessive cost. Modern archaeology does not support Herodotus's depiction of enslaved labor. The worker villages show organized, state-sponsored employment, not slavery. Burials show respect, not mass graves. Ration records show systematic provisioning, not starvation. Herodotus's machines made of wooden planks, interpreted by some scholars as cranes or levers, are not depicted in tomb paintings. No archaeological evidence of such machines exists. The description is ambiguous enough to fit multiple interpretations, none verifiable. This is the problem with second-hand testimony transmitted across millennia. It preserves echoes of truth mixed with elaboration, misunderstanding, and cultural reinterpretation. Separating signal from noise becomes impossible. Egyptian sources closer to the 4th dynasty are even more silent. No contemporary texts describe pyramid construction. No inscriptions on the pyramids themselves explain their purpose or methodology. The structures stand mute, their surfaces once covered in smooth casing stones, bearing no technical documentation. Later, pharaohs did leave inscriptions, not describing construction, but restoration. The inventory stela, though disputed in dating, refers to Khufu discovering the Sphinx and Great Pyramid and restoring them. The language is restored, not built. Mainstream Egyptology attributes the inventory stela to the 26th dynasty, 664 and 525 BCE, more than 2,000 years after Khufu. The stela is therefore considered mythologizing, not historical documentation. Later priests, seeking to glorify Khufu, invented stories of his restoring ancient monuments. But the choice of language is revealing. Why restored rather than built? If inventing glorious deeds, why not credit him with construction, the greater achievement? One reading. The stela preserves a tradition, accurate or not, that the monuments predated Khufu, that his reign involved repairing, renovating, or completing structures already ancient. This reading cannot be confirmed. The stela's late date undermines its authority as historical source. But it contributes to the pattern of textual ambiguity. Egyptian sources do not clearly state who built the pyramids, when, or how. The papyrus silence is not unique to pyramids. Other monumental projects lack detailed documentation, but the scale of the silence is proportional to the scale of the achievement. Small temples have sparse records. The Great Pyramid has none. 50,000 documents. Not one blueprint. The ledgers catalog bread and copper. The archive remains silent on methodology. Too organized to be myth, too strange to be history. The silence can be as revealing as inscription. What a civilization chooses not to explain sometimes matters more than what it proclaims. Egypt chose not to explain the pyramids in writing. That choice, preserved across 4,500 years of administrative continuity, demands consideration. The record lists every chisel issued, but not this. The calculations catalog grain rations down to the loaf, but not the method that moved 2.3 million stones. The papyri speak volumes through their silence. And what the papyri don't say, the restorations do. 200 years after Khufu, the pyramids began to fail. The pyramid of Userkaf, 5th dynasty, partially collapsed during construction. Engineers resorted to rubble fill, loose stones packed into the core, to stabilize the structure. The precision of the 4th dynasty was gone. The casing stones fit poorly. Mortar was required to bind them, compensating for dimensional irregularities. The pyramid of Neferirkara, also 5th dynasty, was never completed. The core stands exposed, showing the internal construction method. Rough limestone blocks, uneven courses, gaps filled with smaller stones and debris. The structure lacks the tight-fitting, megalithic precision of the Great Pyramid. By the 6th dynasty, pyramid construction quality had deteriorated further. The pyramid of Pepite-Sekun shows subsidence, cracking, and structural instability. Modern excavation reveals internal voids where rubble fill has shifted. The casing stones where they survive are smaller, less precisely cut, bound with mortar. These later pyramids were not modest projects. Pharaohs invested resources, mobilized labor, attempted to rival the 4th dynasty achievements. They had the same quarries, the same Nile transport, the same administrative systems. What they lacked was the method. This is not economic decline. 5th dynasty Egypt maintained trade networks, built temples, commissioned statuary, and preserved administrative bureaucracy. The civilization was not collapsing. It was forgetting how to cut stones to micrometer tolerance, forgetting how to position blocks without mortar, forgetting how to maintain structural integrity at monumental scale, forgetting how to encode astronomical alignments and mathematical constants. The degradation is technical, not financial. Later, pharaohs had resources. They lacked knowledge. Inscriptions from 5th Dynasty restoration projects survive. These are not construction records. They are repair records. Texts describe maintaining older structures, replacing damaged casing stones, reinforcing weakened passages. The language is revealing. The inscriptions describe preserving what ancestors built, not replicating their methods. The techniques are presented as inherited, not developed. The monuments are treated as legacy, not as reproducible achievements. One inscription from the reign of Shepseskaf, last pharaoh of the 4th dynasty, describes completing his predecessor's pyramid. The language suggests the project was unfinished, requiring Shepseskaf to bring it to completion. This may indicate that even within the 4th dynasty, pyramid construction knowledge was fragile, dependent on individual expertise. If mastery was concentrated in a few specialists, their deaths would create knowledge gaps. Successors might lack the comprehensive understanding necessary to maintain standards. Techniques would degrade incrementally, each generation slightly less skilled than the previous. This model explains gradual decline, but not sudden collapse. The 5th dynasty decline is not incremental, it is dramatic. Precision drops from millimeters to centimeters. Construction methods shift from tight-fitting blocks to rubble fill. The change is stark, suggesting not gradual forgetting, but abrupt knowledge loss. Abrupt loss implies disruption. War, plague, political upheaval, or the death of a master architect without trained successors. Any event that interrupts transmission causes knowledge discontinuity. But 5th dynasty Egypt shows no evidence of major disruption. No invasions, no plagues, no political collapse between 4th and 5th dynasties. The transition is relatively smooth. Administrative continuity is maintained, yet pyramid construction quality collapses. This suggests the knowledge was never broadly distributed. It resided in a small cadre of specialists. When they died, retired, or stopped training successors, the knowledge died with them. Later attempts to revive pyramid construction in the Middle Kingdom, circa 1700 BCE, show continued decline. Middle Kingdom pyramids are smaller, built primarily of mud brick with limestone casing, structurally weaker. Many have collapsed entirely, leaving only rubble mounds. The decline is 1,500 years into the future from the 4th dynasty. By this point, the methods are completely lost. Pyramids are built from cultural memory, symbolic continuity, not technical mastery. If Egyptian engineering advanced over time, the trajectory should rise. Early experiments should give way to refined techniques. Prototypes should improve over generations. The oldest structures should be the crudest. The newest should be the most sophisticated. The opposite occurred. The oldest is the most sophisticated. Every attempt to replicate it produced inferior results. The trajectory is inverted. This inversion is the restoration testimony's central claim. Later, pharaohs did not build new pyramids. They attempted to restore, replicate, or approximate what the 4th dynasty achieved, and they failed. The attempts are documented. Inscriptions state the intention. The results demonstrate the failure. Techniques were attempted and abandoned. Precision was pursued and lost. Scale was imagined and reduced. The testimony is negative evidence. What later builders could not do reveals what 4th dynasty builders knew, and what they knew exceeds what later generations retained. Knowledge does not usually vanish in 2 centuries. unless it was never fully transmitted. Mastery takes generations to develop, but can be lost in a single generation, if not written, codified, and broadly distributed. Egypt's choice not to document pyramid construction methods ensured those methods would be lost when the specialists died. The textual silence guaranteed knowledge discontinuity. This was either deliberate, sacred knowledge restricted to initiates, not to be profaned by writing, or unintentional, practical knowledge assumed so common it needed no documentation, only to be forgotten when specialization ended. Either way, the result is the same. 200 years later, they had forgotten how. The inscriptions say restored, not built. Mastery does not vanish in 2 centuries unless it was never theirs to begin with, unless the 4th dynasty inherited rather than developed, unless the knowledge was received complete, applied once, and then gradually lost as the source was forgotten, and the inheritors lacked full understanding. This interpretation aligns all the evidence. The sudden appearance of complete mastery, the lack of practice structures, the immediate degradation after the apex, the textual silence on methodology, the restoration language in later inscriptions. If the 4th dynasty built on inherited knowledge, everything fits. The knowledge was old when they used it. They applied it without fully understanding its derivation. When the specialist died, the knowledge was incompletely transmitted. Later, generations retained fragments, enough to attempt construction but not enough to succeed. The restorations failed. The original stands, and beneath it, something older, too organized to be myth, too strange to be history. The evidence does not prove inheritance, but it strains the alternative. If the 4th dynasty developed the knowledge independently, why does the development leave no trace? Why no incrementally improving structures? Why immediate perfection followed by immediate decline? The restoration testimony does not answer. It only catalogues the attempts and documents the failures. The inscription says restored. The structure remains, and the question persists. Ground-penetrating radar surveys of the Giza Plateau, conducted from the 2000s onward, reveal what sand conceals. Chambers beneath the surface, voids in the bedrock, structural features that predate the pyramids visible above ground. The plateau was not virgin desert when the 4th dynasty arrived. It was prepared. Bedrock leveling extends beyond the pyramid footprints. The entire plateau shows evidence of surveying, grading, and subsurface engineering. This is not natural geology. Limestone bedrock erodes irregularly, creating uneven surfaces, cavities, and fissures. The Giza bedrock shows systematic modification, leveled areas, filled voids, reinforced zones. Seismic tomography, using sound waves to map subsurface density, reveals stratification patterns inconsistent with single-period construction. The bedrock preparation shows layering, suggesting work conducted over extended time periods or using different methodologies than the surface structures. Natural limestone cavities exist throughout the region. But natural cavities are irregular, formed by water dissolution along fracture lines. Some subsurface features at Giza show geometric regularity, straight walls, right angles, uniform dimensions. These are excavated, not eroded. The purpose of these subsurface chambers is unclear. Storage, ritual space, structural reinforcement. The radar cannot determine function, only presence. The chambers exist. Their origin is uncertain. quarrying activity leaves signatures, tool marks, debris piles, access ramps. Some subsurface areas show these signatures. Others do not. Areas of prepared bedrock with no evidence of quarrying tools or extraction debris suggest different modification techniques or removal of all traces. The bedrock beneath the Sphinx shows anomalies consistent with the weathering evidence discussed in Claim Sartha 3. Subsurface chambers and passages extend beneath and around the Sphinx enclosure. Some align with the Sphinx temple. Others extend in directions that serve no apparent purpose related to visible structures. Ground-penetrating radar cannot date subsurface features directly. It detects density variations, voids, and material boundaries. Determining when a chamber was excavated requires accessing it, examining tool marks, recovering datable material, or analyzing contextual stratigraphy. Most subsurface chambers at Giza remain unexcavated. Egyptian authorities restrict invasive archaeology at the site. Non-invasive surveys provide tantalizing data, but no definitive answers. What the surveys do confirm: the plateau was engineered as a unified site. The bedrock preparation is not localized to individual pyramid bases. It extends across the plateau, suggesting a master plan implemented before surface construction. If the plateau was prepared during the African humid period, when rainfall was higher and erosion more active, this would explain subsurface weathering patterns, inconsistent with 4,500 years of desert conditions. The foundations would show exposure to wetter climate, because they were exposed during that climate. If the pyramids were then built on these pre-prepared foundations during the 4th dynasty, the surface structures are dynastic, but the site engineering is older. The visible monuments are Egyptian. The invisible infrastructure is pre-Egyptian or proto-Egyptian, dating to a period before recognizable dynastic culture emerged. This interpretation cannot be confirmed without excavation. It also cannot be dismissed based on current evidence. The subsurface anomalies exist. Their age is uncertain. Their purpose is speculative. The possibility that cannot be confirmed and cannot be dismissed. Giza was not selected for pyramid construction. It was inherited as a location already surveyed, already graded, already encoded with astronomical and geodetic knowledge. The 4th dynasty built monuments on foundations prepared by predecessors, whose identity remains unrecorded in the archive. This is the Subsurface Anomaly Catalog's final entry. The radar sees what the sand hides, foundations older than the pyramids themselves. Someone prepared this ground before Egypt arrived, too organized to be myth, too strange to be history. The claims accumulate, the record remains fractured, and the archive offers no final answer. 10 claims, each rooted in measurement, artifact, or administrative record. Each presenting evidence that cannot be confirmed and cannot be dismissed. The weight inventory paradox, the tolerance ledger, the bedrock weathering report, the geodetic coordinate catalog, the labor ration deficit, the copper tool inventory gap, the stellar alignment archive, the papyrus silence protocol, the restoration testimony, the subsurface anomaly catalog. Individually, each anomaly can be explained. Collectively, they form a pattern too organized to be myth, too strange to be history. The administrative record shows precision. The timeline shows paradox. The official catalog remains unchanged. Egypt recorded what it chose to record. It documented grain and copper and worker shifts with bureaucratic thoroughness. It left the methodology of its greatest achievement undocumented. The silence is selective. The absence is deliberate. The pattern is consistent. The stones remain. The measurements remain. The anomalies remain. And the questions persist across 4,500 years of sand, time, and interpretation. The record shows perfection first, then decline. No practice structures, no improving trajectory. Mastery appearing complete, applied once, and immediately degrading. This is not how civilizations learn, unless they did not learn it, unless they inherited it. The possibility cannot be confirmed. It also cannot be dismissed. The evidence is physical. The erosion patterns, the coordinate precision, the astronomical alignments, the subsurface preparation, these are measurable, verifiable, independent of historical interpretation. What remains uncertain is the source. Where did the knowledge originate? Who surveyed the site? Who encoded the constants? Who prepared the foundations? The archive does not answer. The papyri remain silent. The inscriptions describe restoration, not construction. The methodology is absent. The specialists are unnamed. The transmission is broken. What survives is the outcome. 2.3 million blocks, positioned to millimeter tolerance, aligned to celestial precision, encoding mathematical constants discovered millennia later, built in 20 years or less, never replicated. The catalog remains open, the archive incomplete, the investigation documented but not concluded, 10 claims examined, none definitively proven, none definitively refuted. The evidence exists in the space between confirmation and dismissal, where measurement meets mystery and precision encounters the unknown. The Great Pyramid stands. The questions endure. And the administrative record, exhaustive in its documentation of bread and copper, offers no explanation for the knowledge that moved mountains, too organized to be myth, too strange to be history, cannot confirm, cannot dismiss. The catalog remains open. Good night.